Well,
Okay.
aloha, everyone. Aloha. Welcome to our Awesome Light Exploring the Sun and Stars live Q&A. How's everyone doing? Thanks so much for joining us today for our special event to cap off MKO at Home Astro Day edition. I'm DC from B93, B97, a radio station here in Hilo. In fact, we're in our studios, literally in our studio, so anything can happen. And let's meet our panelists. We are here for our panelists today. First of all, joining us, I believe down in the lower corner over here, is where we're so happy to have with us Dr. Claire Raftery. Dr. Claire Raftery is the Director of Education and Public Research, the National Science Foundation's Inouye Solar Telescope. Dr. Raftery is a solar physicist and science educator, originally from Ireland, having researched solar flares and coronal mass ejections. She is now the Director of Education, Outreach, and Communications for the National Solar Observatory, which is the organization responsible for building the National Science Foundation's Inouye Solar Telescope. Claire loves telling science stories and is dedicated to providing equitable opportunities in STEM for students from all walks of life, especially those who are underrepresented in astronomy. What an introduction. Claire, how are you?
Hi, it's great to be here. Thank you so much for having me today, DC. How are you doing?
We are doing great. You are in the beautiful city of Boulder, Colorado, correct?
I am. I'm quite a ways away from you at the moment, but I consider myself very lucky in that I get to split my time between Boulder, Colorado and Maui, Hawaii. That's where NSO has its two offices. And so, you know, it's a tough life, but somebody's got to do it, you know?
Absolutely. It's beautiful. Boulder is beautiful. And speaking of Maui, joining us today also from the island of Maui is Dr. J.D. Armstrong, Maui Technology Education and Outreach Specialist, University of Hawaii's Institute for Astronomy. J.D. is the project scientist for the Phoenix Telescope North. That's the world's largest telescope built for education and for outreach. J.D. works to create the scientists of the future, and he does it so well too. I've seen him in action at our Astro Days that we have here every year. And so JD, there's a nice bit of Astro Day continuity going on having you here. How are you, my friend?
It's doing great. Thank you. I'm glad to hear that you're doing well. Yeah, it's really sad that I don't get to go over to the Big Island for Astro Day. I always enjoy meeting with you and the rest of the community over there. And so, yeah, the Institute for Astronomy is part of the University of Hawaii, and we have branches here on Maui and also in Hilo to support the telescopes of the community in those locations. And a quick comment on the Phoenix Telescope North, that's owned and operated by Las Cumbres Observatories, global telescope network. They do a lot of, they give a lot of observations to the kids in Hawaii so that students can do real science around here.
Oh, that's great. Thank you for mentioning that. I don't know if I had that in my introduction or maybe I skipped over it, but that's very important. We get okay.
Yeah, and one last thing, I do want to send some birthday shout outs to my niece Kelsey, happy birthday, to my mom, happy birthday, and also to my nephew Gavin. Love you all.
Wow, all happening within the next couple of days, huh? Fantastic.
Yeah, it's just one right after another.
Why not, JD? Well, joining us also here, right here in my neighborhood here in Hilo, Hawaii, we are happy to have with us the astronomy educator, Miss Emily Peavy. Emily, our astronomy educator at Imiloa Astronomy Center of Hilo, University of Hawaii at Hilo, absolutely loves talking to people about stars, space, galaxies, which is why we're so glad to have her with us, and her adorable dog, Kiki. Emily, how are you?
I'm doing great. It's so wonderful in order to be here. I do have Kiki in my background. She wasn't able to be with us today, but she's in her picture over there.
Yay.
Yes, representing Imiloa Astronomy Center here in Hilo. Imiloa Astronomy Center is a museum, planetarium, and science center that is set up to encourage education that accounts for culture, science, and community inclusion here on the Big Island of Hawaii. And I love talking about astronomy as my role there.
Excellent. And Imiloa, of course, the jewel of Hilo. It's always so nice to see it as we're driving in, and we're real proud of Imiloa. So thank you for representing them here for us today. I guess we should start off with the hard questions first. And Claire, I think we'll go to you on this one. Claire, should we look at the sun ourselves?
That is not a good idea. Not if you're a fan of your eyesight. No, we should never look directly at the sun, at least not unprotected. So there are some safe ways to look at the sun. If anybody may have seen a solar eclipse, you may have gotten your hands on some pretty cool eclipse glasses, which may look flimsy. They're usually made out of cardboard and foil, but actually that foil is super important. And even before you use them, you should make sure there's no cracks or holes or anything in that foil, because that's how we make sure that most of the light from the disk of the sun is actually blocked out. And so using eclipse glasses directly on our eyes, or if you have a telescope or binoculars, you got to put a solar filter on the front of that. What we like to say is you got to put the protection between the camera and the sun, and whether the camera is your eyes or your telescope or whatever it might be, whatever is receiving the light. That way, almost all of the dangerous, intense light coming from the disk of the sun gets rejected. Now, there are some times when it's actually safe to look directly at the sun, but only very minimal. So during the period of totality, during a total solar eclipse, those 2 or 3 minutes, it's actually safe to look in the direction of the sun without any special solar filters, because the moon is our solar filter in that case. The moon itself is actually blocking out all of the light from the solar disk, which is the really intense stuff that would do damage to our eyes. And so that's why we get to see the beautiful corona, which is what's the sort of fluffy stuff around the edge of the edge of the solar disk that normally we can't see, because the solar disk is so bright and so intense, it just completely washes out everything in the corona. So the answer is no, but.
No, okay, the answer is no. I don't know if you folks are, or maybe I'm the old one here. 1991 here on the Big Island, we had a complete total eclipse. It was just the most amazing thing to see, having it be like 7:30 in the morning and it suddenly go dark. It was just a mind-blowing experience. So it's pretty amazing stuff. We thank you, Claire. Thank you so much. We actually are getting some questions from some of our viewers. And JD, if you don't mind, I have one for you if you want to start off. JD, this comes from Katie. Katie is 14 years old, all the way from Pittsburgh, Pennsylvania. Thank you, Katie. Her question is, why are the many different stars made of the same gas?
Oh, well, because they're made from the same cloud of gas. Let me share my screen here. All right. And
oh, it's nice.
Yeah, so this is a picture of the Eagle Nebula that was taken using the Las Cumbres Observatory, one of the telescopes on that global network. And you can see the wing of the eagle here and the body, and it's holding a fish. Well, all of the stars are made from the same cloud. So this cloud is currently turning into stars. Stars are forming from this cloud. And so they'll all be made of the same stuff as that cloud. And all these clouds are made of mostly hydrogen and helium. That's because that's all there was in the beginning of the universe, is hydrogen, helium, and trace amounts of lithium. And so once you form stars from that cloud, they're all going to be made of pretty much the same stuff.
Interesting, interesting. Thank you very much, JD. Thank you. Emily, we got a question for you. Oh, Emily, maybe I should have brought this up earlier too. Maybe when we're introducing you, I hear tomorrow is the International Day of Light. Can you tell us a little bit more about that, Emily?
Yes, so the International Day of Light is a celebration all around light. And light is so important. It's how we interact with so many things around us. It's how astronomers get all the information that we have. What makes tomorrow special is the anniversary of the discovery or the invention of a laser, when we were able to harness light in a very, very specific fashion. And that's what makes May 16th so special. But here in astronomy, as I mentioned, we love light. Just about everything that we understand about the universe from the very beginning of time, when we first started looking at stars, comes from light. Electromagnetic radiation, that's the really big, complicated word for what light is. And light comes in many different types of forms. You have radio light, you have X-ray light, you have some millimeter light, and of course you have the light that we can see with our naked eyes.
Fantastic. International Day of Light tomorrow, folks, on May 16th. Thank you so much, Emily. Claire, we have a question from Alyssa, age 10, from Konawaina Elementary on the west side of the Big Island. Claire, she asks, what special instruments do astronomers need to study the sun?
That is a great question, Alyssa. Thank you. So astronomers study the sun using a whole variety of cameras, and I'm actually going to follow in JD's footsteps here. I'm going to share some pictures of the sun in all different kinds of light. So each of these requires not only a very special camera, but a very special technique for being able to study the sun. So everything from using cameras with special filters on the front, we use films that block out sunlight. We use for some of the higher energies. So up here we have some X-rays and even gamma rays. The sun produces gamma rays. We have to use really innovative techniques. So I used to work for a mission called the Reuven Ramati High Energy Solar Spectrograph Imager. I always get that. It's quite a mouthful. And it was pretty interesting. It actually had two grates that rotated in parallel, and because of the photons that they were trying to capture had so much energy, we couldn't just use a regular camera. They would just burn right through the camera. And so it was they used these two special plates to almost cast a shadow on each other, and then we had to do all of this complicated mathematics to double back to see pictures like this to figure out where the X-rays and the gamma rays were coming from. But the sun produces light in pretty much every wavelength of the electromagnetic spectrum, and so depending on the kind of light that we're using, we have to use a very different kind of camera. On the other end of the spectrum, we have radio waves and microwaves, and to study those we need just big dishes, and so big dishes like well, not necessarily that you see on the side of your house. They're much bigger than that. They're many feet across, but they're used to capture radio waves. And so depending on the energy of the light that we're looking at, the different cameras can have a different effect. The wavelength of radio waves is so long that we're able to just use big dishes, big radio dishes, and often multiple dishes at the same time that we can string together to be an even bigger one called an interferometer. Then if we look at something like the ultraviolet wavelength, so you can see here the sun in ultraviolet light is beautiful. It has all this structure and detail, and we compare it to here with the visible sun, which is what we have, our eyes are tuned to. And of course, it's much simpler. There's very little excitement going on, and who knows, that might be why our eyes are tuned to that. But we have to use very different cameras to pick up this kind of light, and that's where those films that I mentioned come into it. So I put films in front of our cameras and our optics to be able to tune out a lot of the light rather than tuning it in. So we make sure that extra light is not making its way into the telescopes. The telescope that I work for, the Inouye Solar Telescope, actually I have some pictures from it right here. These are pictures from, let me see if I can make this play. There we go. So it's the same picture. This one is the full field of view. This one is just zoomed in. And these are the highest resolution pictures of the solar surface that we have ever seen. We released these earlier this year, and this came from Hawaii. These were taken on the island of Maui. And this is really going to change the way we understand our sun forever. So these were taken with a camera called a visible broadband imager. And so it tunes a very special portion of the sun's wavelength into the camera, and it makes sure none of the rest of the light gets in. So it can really make sure everything is crystal clear and super focused to get these beautiful crystal clear images. So.
That's fascinating. That is fascinating. That kind of leads to our next question. And you may have sort of answered this in some way too, but how do solar telescopes differ from, like, say, the telescopes that we have on Mauna Kea? Pretty much, I think you kind of said it in a way, but
well, there's other things to take into account too. It's a really interesting question because there's so many different facets. It really depends on the kind of telescope that we're using. But if you compare the ground-based telescopes that study predominantly visible light, so the likes of the Inouye Solar Telescope, and compare them to the telescopes that you have on Mauna Kea, a big part of what we do is we have a lot of light that we're collecting from the sun. That's a really big difference between nighttime telescopes and daytime telescopes. if you were to point, you know, a large Gemini-sized telescope at the sun, that would be so much light that it would do serious damage to the actual elements of the telescope. You know, who knows what would happen, but I'm not saying it wouldn't go on fire. But I certainly don't think that we would be allowed to try it anytime soon. And so when we're building solar telescopes, we have to take that into account. So we have this giant light bucket. So the mirror on the Inouye Solar Telescope is more than 13 foot across. And so I don't know if anybody has ever played with magnifying glasses as a kid, where you've got it outside in the sun and you're able to burn things. Well, imagine if your magnifying glass was 13 foot diameter and how much light you'd be able to do and the kind of damage that you'd be able to do. So we build a telescope with heat control and thermal control as one of the main priorities. And so making sure that everything is really well balanced and is well cooled and has lots of airflow, but not so much airflow that it impacts the quality of the images, and making sure that we have all of the right materials that are not going to expand and contract too badly, and, you know, keep everything nice and solid and monitored. Because not only do you not want everything to go on fire because it's so big, or melt or do damage in any way like that, but when you're taking astronomical pictures, you have to keep your temperature really, really, really steady, because otherwise you get all kinds of shimmery mirage-like effects. I don't know if you've ever been driving down an asphalt road and you see sort of the shimmery feature on the road in front of you. Well, we get that in telescopes if there's too much heat in the room. So you got to keep the temperature super solid, and so we can't have any big fluctuations in temperature. So I would say that the temperature difference and the amount of light that we collect is probably one of the biggest differences in nighttime telescopes versus daytime telescopes.
I see. Now we hate to feel like we're grilling you, but we're actually getting some questions about your image that you showed us, the sun image. Someone is asking, what is the scale of that sun image you were showing us? What was in terms of scale?
That's a great question. So let me reshare it just so as I can talk to it.
Sure.
So this is, for scale on the Earth, one of these cells is about the size of the whole state of Texas. So they're pretty huge by comparison. The whole thing from side to side is about 7,000 kilometers. And so, yeah, the size of the state of Texas would fit approximately into one of these. And then for some other comparisons, see these really small details. Maybe this one is easier to see in here. Can you see these the spots in here, in between the little tiny white spots? They're about the size of the entire island of Maunakea.
Wow.
So yeah, these are pretty enormous things. They look like teeny tiny details to us, and they really are by comparison to what we've seen before. If you look at this in some of our older telescopes, it's really blurred out. You can't see any of this stuff. When we saw these pictures the first time, everybody was, you know, blown away at how much detail we were able to see. And that's definitely a testament to the team who are building the telescope. But yeah, the fact that we're able to see things down as far as 13 miles across on the sun, when you think about how far away the sun is from the Earth, that is, it's quite detailed. So hopefully that helps to put it in context a little bit for the size.
Absolutely, absolutely. Thank you. That is so fascinating. So fascinating. Okay, JD, it's your turn. Back to you. And hang on, we have one for you too coming up, Emily. But JD, Alyssa from 10 years old from Kona is asking, compared to the sun, what is the next largest star? So the sun is a star. So what's the next largest, or the next largest star, I guess?
So, well, the sun isn't actually the biggest star. So
maybe the nearest star? Should we go with that instead? Or
well, the nearest star, the nearest star would be Proxima Centauri, which is a little tiny red dwarf star. And if we were able to see stars that faint, then we'd be able to see it from here in Hawaii, because we're far enough south. So yeah, the sun is a star, and stars range in mass from about 8% of the sun to hundreds of times the mass of the sun. And so, of course, we say that the sun's a middle-sized star. I don't know, maybe Claire, can you help me understand how that's a middle-sized star? Emily?
I don't know if I'm going to be able to help you understand, but I will use a description that really helped me when I was trying to understand this. So when we study the stars, you know, we really only have a snapshot of what every star is doing for a teeny tiny speck of time compared to the whole lifetime of the, like the
Oh, yeah.
sun is 5 billion years old and it still has another 5 billion years or so to live. And so somebody described it once as, if you were able to take, if you're an alien coming from outer space and you're able to take a snapshot of every human on planet Earth in 1 second, then you would only know a little bit about every single human, but you'd have a pretty good scope of understanding of generally how humans work, how tall they are, how short they are, how long they live, whether they eat food or whether they eat, I don't know, tree bark, or, you know, like what the different behaviors that we have. And, you know, we would be able to see the whole spectrum very generally of the human race. Now, if you're studying any one human, you wouldn't be able to tell very much about that human at all. And so we can think of the same way when we study the universe. So you look at all the stars in the whole universe and you get a tiny snapshot of every single one of them. And then we can say, okay, well, generally we get that they're probably this big to this small and this old to this young. And this is how some of them die. And they, you know, all the different processes. For any one star, you can't really tell that in great detail for a single one, but we know then roughly, okay, well, it's likely because this star looks a bit like that star, then this is the way it's going to live and evolve. And so for the sun, by studying all of the stars in the not in the human race, all of the stars in the sky, we're able to say that the sun is roughly in the middle of its lifetime. We know that it's a G-type star. We know that it's sort of a pretty average, moderate size. It's not too big, it's not too small. It's just the right kind of star to be able to harbor human life. So for that, we're very lucky. So I don't know if that was any help,
so
JD,
much.
or if I just sent you off on a tangent.
Down a wormhole, here we go. No, that was fantastic. Thank you. But now, Emily, we don't want you to think we're forgetting about you. So we have a question for you, Emily. You know, at night, especially here in Hawaii, when we go out, and if it's that rare time in Hilo where there's no clouds, the stars are just so beautiful. I guess this is just a basic question. How many stars can we see in the night sky without a telescope? Emily, would you want to take that question? Is that a Emily type of question?
So on the clearest, best night of observing, if you could actually see the entire sky around us, so even everything that's below your feet, below the earth, you could see everything around you. Our human eyes are capable of seeing about 6,000 stars. Now, on a given night, just clear, dark, everything that's above your horizon, it's a bit closer to 2,000. But as you were saying, here in Hawaii, we often get beautiful, dark, clear skies. If you just get a little bit away from Hilo and get outside of the clouds, you get absolutely gorgeous skies.
Oh yeah, once your eyes adjust, it's just so beautiful. And you always think, I'm seeing the entire universe, but really we're seeing about what, 2,000 stars, you say, huh?
2,000 stars, but that's, when I'm saying that, I'm referring to only the stars that your eyes are able to make out as individual points. So that means you're seeing the point source of the star. However, especially during the summer months in Hilo, we get a fantastic view of the Milky Way. And when you are looking at the Milky Way, it looks like gray fuzziness stretched across the sky. It's called the Milky Way because it looks like spilled milk. Well, that gray fuzziness is actually the combined light of millions, even billions of stars that your eyes can't make out as individual points because they're too far away from us. But if you grab a pair of binoculars or if you grab a telescope and you look at that gray fuzziness of the Milky Way through a pair of binoculars or a telescope, you start seeing that Milky Way is made up of thousands and thousands of stars that you can now see once you give your eyes a little bit of help.
That's amazing. That is such a great sight to see the Milky Way, because at first you think it looks just like a cloud in the sky, but it's not. It's like you said, those jillions of stars that our eyes can't quite see. But it's fascinating. It really is. Thank you, Emily. Thank you very much, JD. We've got a question for you, JD, from Peter, and he's asking: is it possible to detect sunspots on another star? We can detect them on the sun, of course, but can we detect them on another star, or are they too far away? Thanks, Peter, for the question.
Yeah, it's kind of a trick how we do that, because when we look at other stars, we with only a very few exceptions, we don't see any size. We don't see any of the resolution that we get with our own star. But what we do is we measure the brightness very carefully. And as a sunspot comes around, it'll change how bright that star looks, because you've got a sunspot or a star spot is this dark spot on the star. And so by observing the brightness and measuring it carefully over time, you can actually see them rotate in and out of our field of view. And therefore we can observe them. And one of the scientists over in Manoa does this type of thing. By doing that, you can measure how fast the star is rotating.
Fascinating, fascinating.
Can I chime in on that one too?
Oh, yeah.
Sure,
the other
Claire,
other thing that happens is we study the same thing but in reverse. So we can actually take the sun in all its glory and resolved surface, and then we can shrink it down and pretend it's a single spot, and then we can watch its behavior. So then we can identify what we're seeing as behavior on other stars and say, that's how that gets connected to it. So we use the sun as like our standard candle for the rest of the universe often.
We want to thank that, by the way, not Peter, that was Nicholas who asked that question. So thank you very much, Nicholas. And sorry I misread that. Okay, I'll take the blame for that one. Gang, if I can ask, maybe to start with Claire, Imiloa Astronomy Center. Why, our talk here today is awesome light, the exploring the sun and stars. Why is it important to study the sun and stars? I know it's kind of a pullback question, but maybe you can tell us what your facility does to support the study of the sun and stars. And maybe Emily, we'll go with you first. Imiloa, the hometown team.
Yeah. So why is it important to study stars? And I think that goes back into a very essential component of exploration. And it's expressed here in Hawaii and around the world, that whenever you are exploring, whenever you are thinking about going on a journey to learn something new, you're going to think about where you're going to go. But before you think about where you're going to go, you must first understand where you are. But to gain a better understanding of where you are, you must always be starting your journeys by thinking about where you came from. You need to start your journeys by thinking about your past, your history, what brought you to the moment where you are right now. And that is why astronomers really like studying the stars, because if we think back to the very, very beginnings of the universe, all cosmologies, especially the Big Bang or any other cosmologies, the universe starts with essentially nothing. And in astronomy cosmology, that nothingness begot clouds, and then those clouds created the very first stars. And it was those stars that were able to create the elements of the universe. At the Big Bang, only two elements were created, and that was hydrogen and helium. And there's little bits of trace elements, but that was mainly the only two. But we're not made out of hydrogen and helium. We got a bunch of other stuff in us. And over the course of time, inside the center of stars, stars are making their light and heat and energy by changing those simple types of elements into more complex types of elements. And after 14 billion years, there are now enough complex elements, oxygen, carbon, nitrogen, calcium, all this stuff that is able to make us here on the planet Earth. So when we look to the stars, we're looking towards our own origins. And we recognize that we are stardust and we are products of the universe.
Now I'm going to start singing that Joni Mitchell song, Woodstock. We are stardust. No, but you're right.
Yes.
That's great. What I enjoy about Imiloa is how you folks are able to also kind of tie in the Hawaiian studies of how our voyagers came to Hawaii using the stars, and tying that all together. That's always made adds an extra dimension for us here in Hawaii to our studies of the stars by how our ancestors got here. That's great. Let me, if I can ask the other members of our panel here today, JD, maybe tell us about how your facility, what you do to study the support of sun and stars while you're out there on Maui.
Okay, so I'm sort of loosely tied to kind of every telescope on Haleakala, and more directly tied to the Falks Telescope North. So I do want to talk about programs like Atlas and Pan-STARRS. And these are projects that detect asteroids that could come in and hit us. Dinosaurs were wiped out by a big rock hitting the Earth, and we don't want to follow their lead. And so these telescopes are designed to find those asteroids. And then one of the things that I do with students, middle school and high school students, is we use the Falks Telescope North to do follow-up observations of the detections that Atlas and Pan-STARRS have. And so then these students are helping save the world, and they end up getting on these publications. And by the time they're applying to college, they can say, yeah, so I was on half a dozen Minor Planet Center circulars as a published author. And so that's, hopefully that kind of ties everything together, except for the Air Force, which acts like, think of air traffic control for satellites. That's what the Air Force mainly does with the observatories here on Haleakala. And then, of course, this would be a great time for us to lead into Claire, which with the National Solar Observatory, which is here on Haleakala.
Indeed, yes, we have the Inouye Solar Telescope also on Haleakala. So the National Solar Observatory does exactly what it says on the tin. We study the sun. We have one star that we really focus all of our time and energy on. And then we're able to use that understanding, like I said earlier, for expanding to the rest of the universe. But our understanding is focused on the sun. And that's for a number of reasons. And a big part of that is to better understand what makes the sun dynamic. So the sun is explosive. It is constantly moving and churning and erupting. And the video that I showed earlier on, where you could see all those cells bubbling away, that's normal. That's the way the sun is all the time. And you may have heard of the phrase coronal mass ejection or solar flare, and they're the technical terms we use for solar explosions, essentially. And when you have solar explosions, they actually can have an impact on the Earth. So if they're directed towards the Earth in just the right kind of orientation, sometimes they have beautiful impacts, like the aurora borealis and the aurora australis. They're actually caused by the sun, but they can also have not so great impacts as well. So we can have issues with electrical grids. They can cause challenges with communications satellites and with GPS systems and so on. And so a big part of solar physics is to understand what's driving the sun. And that kind of breaks down into a bunch of different areas, like subset areas, but the sort of big underlying question is understanding the sun's magnetic field. The magnetic field drives everything. It causes all the explosions, it causes all the dynamicism, everything that happens on the sun is driven because it's magnetic. And so the Inouye Solar Telescope is really dedicated towards that. And we have other facilities. We have the Global Oscillations Network Group, or GONG, which is a series of 6 telescopes that are located all the way around the world, because of course the planet Earth rotates. And as you rotate the Earth, the telescope moves out of the view of the sun. If it's at nighttime, you can't see the sun. You can't do solar astronomy if you're in the middle of the night. And so we have telescopes that are dotted all the way around the planet. So one of them is constantly rotating into daylight at all times. And so they have special cameras on there to be able to study the sun's magnetic field. They also study other parts of the sun's atmosphere. But really what's driving a lot of this is better understanding the sun's dynamic behavior, and specifically the more sort of fun stuff, the explosive behavior, because that has a very direct impact on our life here on Earth.
The explosive stuff, that's the fun stuff. Thank you so much, Claire. Thank you very much, Claire. Panelists, we have a question from Matthew, and this is actually for all of you, so we want to go around. Matthew's asking, how do you see astronomy impacting the lives of kids and young adults that you interact with? Maybe we'll start with you, JD, since you helped to create the scientists of the future. How do you see astronomy impacting the lives of our young adults and young people?
Well, from what I do, it teaches them to think. That's one of the main things that I see. A lot of people forget that really, you start science with data. You don't go in thinking you know the answer. And astronomy in Hawaii, at least, it's a way for students to really get professional grade data, work on a project, and learn how to do that, and learn how to follow the scientific process. The other thing that I see is it really kind of gives us a connection to the universe. You know, most people get to look up at the universe and appreciate its beauty. Here in Hawaii, we've got a bit better view, even if we're not using the telescopes. But when you start using the telescopes and math and physics, you can make an even deeper connection. And I remember one of the students I was working with, he was up at the Institute for Astronomy, and it was late and he was about ready to head home. We were out in the parking lot, and his project was on one of the moons of Saturn. And he'd been looking at dots on a screen for hours, just trying to detect the position of this one little tiny moon. And so we're out there in the parking lot, and I point up at Saturn and I say, "That's Saturn." It's like, "Oh, okay. That's your project." He's like, "Oh yeah." And so suddenly it paints this bigger picture of what the universe really is.
Emily, I know Imiloa Astronomy Center does so many great projects with our keiki and different shows. Maybe you can tell us a little bit about how Imiloa interacts with our young science minds.
I want to echo a little bit of what JD said, and that's my specialty is a lot more in education. I just got my master's in education as well, and it's teaching science is supposed to be teaching critical thinking. It's teaching how to interpret information. It's teaching, oh, you learned this, but how much do you trust that you know that? And it's a skill that is applicable in all walks of life, not just in science. Now, specifically in teaching astronomy, I always like to say very sincerely, astronomy is the most universal science. And I say that very sincerely, also acknowledging that it's a beautiful pun, but it's so true. It is the most universal science in that no matter who you are, no matter where you came from, you probably have a connection to the sky, and you probably have a connection to the sun or stars in some way. And so you're able to, in astronomy, you can connect to just about everybody in the world. And in teaching astronomy and education of astronomy, you challenge people to think critically about something in astronomy. It's like, okay, you see the sun during the daytime, and when the sun is up, the sky is blue. Could there be a connection there? Oh, and when you go into nighttime, you see a lot more stars. But when the moon is out, you see less stars, sort of thing. So being able to walk a path of teaching astronomy, which is accessible to so many people, and also encourage that in order to encourage critical thinking skills as well.
That is so good, because critical thinking is just so important, and that's the great thing about education. And it's like you said too, it's very important for our young folks to start off with that mind, that fertile mind. And Claire, would you like to add to that?
Sure. Yeah, I'd like to definitely echo what both Emily and JD have said, and in particular the idea that, you know, astronomy is the great unifier. It really is like one earth and one sky, and I think that is really powerful and has the ability to cut across cultures. There's a few other sort of the other two have sort of touched on a lot of the, you know, the core things. I might add to it in some of the more sort of practical sides of things. So as somebody who had to leave her home country of Ireland to find work at an observatory in a different country, I suppose I would say I'm quite envious of the fact that there are such world-class facilities available across the US, but in particular to the students in Hawaii. I had to, you know, move 7,000 miles to find those kinds of opportunities, and they are right there on your doorstep, and that is so amazing. And so I think the other big part of that is to remember that the majority of people who work at observatories are not astronomers. We definitely have astronomers, but the majority of people who work there are engineers and support staff and accountants and administrators and educators and artists and writers. And we have a whole plethora of people who are absolutely essential to go into making a telescope and an observatory functional and effective. And so, you know, just because you don't want to become a PhD astronomer, that doesn't mean there's no jobs for you in astronomy. There are so many different career opportunities for you across the whole spectrum of different different careers that you could potentially pursue. So it's definitely kind of a unique opportunity in that respect, because you could take your creative writing degree and go apply it to an astrophysics environment, and I bet that's never something that you crossed your mind to be able to do. Or you can do graphic design work, but for explaining the dynamics of different astronomical objects. And so there's all different ways that you can take non-astronomy skills and apply it to this work, because we need everybody to be able to make this field work.
Absolutely, absolutely. So there could be a future for me there too, right?
Absolutely, yeah. People keep telling me we need to start a podcast, so you never know. We'll be calling on you yet.
Okay. We are getting some.
For everyone.
What was that, Emily? I'm sorry. What was that?
I said astronomy is universal, so that means it's for everyone, and everybody can do astronomy, no matter who you are. It doesn't matter how old you are, where you come from. You can study astronomy, and you can be an astronomer, or you can contribute to astronomy in all different ways.
That's fascinating. We have some questions. Let me get to them, folks, if you don't mind. Let's start off. Oh, we have a bunch of them. Let's see. Let's go JD. JD, we have Adam. Adam is asking, how do you observe the sun at night? And that's a serious question he's asking too. It's not being tongue in cheek, but how do you study the sun at night?
Yeah, I think I know who Adam is, and it's a little tongue in cheek, probably.
Oh, it is. Okay.
But yeah, we actually can do that, and the secret is you choose a telescope on the other side of the Earth from where you are. That way, it's in daytime. And so this kind of ties in with a project that Claire mentioned, the GONG group, Global Oscillations Network group. They have telescopes all the way around the world. And there's also a satellite. There are a couple of solar satellites up there that you can watch the sun 24 hours a day using those. And so there are a number of different places where we observe the sun. And do you want to add anything to that, Claire? Or?
No, I think you pretty much covered all of it. I guess only to say that the majority of people who study the sun for a living tend to do it inside at a computer. We rarely actually get to see the sun. So a lot of astronomical data is taken at a telescope, and then we use the internet to be able to pass it around and to share it. So then you can be on the other side of the planet and studying an object that you can't see from where you are because it's on the other side of the sky, like JD mentioned. And so the internet is a wonderful thing.
Yeah,
it is. It is.
I remember a couple times going up to the summit of Haleakala on a clear sunny day to observe the sun, and then hiding in a dark building.
Of course. It's like, wait a minute, I'm supposed to be outside. No, that's great. Let's see, Claire Cassandra is asking, she wants to know, how hot is the sun?
Cassandra, that's a good question, and there is many answers to that question. So the surface of the sun, so first of all, there's not really any surface to the sun. There's the place at which we can stop seeing into it. And I know that sounds really weird, but if you think about a fog bank, if you're in a car and you can see fog in front of you, you don't know exactly when you drive into the fog, you just know all of a sudden you can't see very far anymore. And then you drive out the other side and everything is clear again. And the surface of the sun is really similar. That's because of a thing called opacity. And so if we look at the temperature right there, where we can no longer see into the surface anymore, or sorry, into the inside of the sun anymore, call that the photosphere, which means sphere of light. And that's about 5,500 degrees Kelvin. That might seem really hot for us here on Earth. It's actually pretty cold by comparison, because if we move away from the solar surface and out into space, into what we call the solar corona, we actually start to get temperatures of 1,000,000 degrees and more, 1,000,000 degrees Kelvin. And so but when you're talking about 1,000,000 degrees, it doesn't really matter what your units are, whether it's 1,000,000 degrees Fahrenheit, 1,000,000 degrees Celsius, 1,000,000 degrees Kelvin. It's plus or minus a bit of really, really hot is still really, really hot. So it's still, it's one of those problems in astronomy that we actually don't know what the answer is for. So if any of you have theories, maybe you can come and join us and become the next round of solar astronomers and get your PhD and answer we call this the coronal heating problem. Because if you are standing near a bonfire and you're up close and it's nice and toasty, and then as you move further away, you get colder and colder. But with the sun, the opposite happens, where you're standing near the surface and, you know, bearing in mind that the source of heat from the sun is inside. So the core is where the heat comes from. You would imagine the closer you are, the hotter it would be, but you're standing near the surface and it's 5,000 degrees, and then you move away and it becomes 1,000,000 degrees. And we don't really know what the answer to that is. There's many theories, and we're actually hoping the Inouye Solar Telescope is going to give us some answers to this. But as yet, it remains a big, big mystery in solar physics. So answers on a postcard if anybody has any ideas.
Right on. Our young science minds, that might be the next mystery we try to figure out. Emily, I've got two questions here for you. Let's see, I don't know if we can tie those, but want to thank Cassandra for that earlier question. Sky from Kalapana, Emily, nearby, just south of us here in Hilo, wants to know what is the closest star, which we kind of asked. Maybe Sky just tuned in, but maybe we can answer that. And why do stars twinkle? That would be for Emily.
Oh, okay. I first interpret that you wanted to know what the sky looked like from Kalapana, and I had to think about it first.
Oh.
I want to share with you a portable planetarium, a planetarium that you can put on your laptop, and this is a free program called Stellarium that you can download on your own computer and play with the nighttime sky. So I'm going to share my screen with you and share Stellarium with you.
All right, cool.
And this is the sky tonight at 9 o'clock, and this would be the sky that you could see from Kalapana if you are looking at the sky down there. And so right now we're facing towards the southern sky here in Hawaii at 9 o'clock. And we see the Southern Cross just above the southern horizon. And just next to it, there's these two bright stars, Kamailua and Kamailehope, which are also known as Beta and Alpha Centauri. And we're going to focus on Kamailehope. And this is the Alpha Centauri star system. This is actually a triple star system. So there are three stars. Two of the stars combine in order to make the light here. And then there's a third star that has a really, really big orbit that's a little bit farther off. And this triple star system is the closest star system to our sun and our solar system. It's only about 4 light years away, which means it takes light, the fastest thing in the universe, 4 years to travel from that star to our eyes. Now, a fun thing on a side note, when you go out to look at these stars tonight, you'll notice that the two stars, Kamailua and Kamailehope, appear to have a very similar brightness to them, but these stars could not be more different. Kamailehope is a fairly faint star that's really close to us, only 4 light years away, while Kamailua is a fairly bright star that is a lot farther away from us. It's about 400 light years away from us. So when you go out tonight to take a look at these stars, the light that enters your eyes from Kamailehope left the star last US presidential term, but the star that enters your eyes from Kamailua left the star 400 years ago, before the United States was even a country. But the stars be a very similar brightness. Now, I mentioned Kamailehope, the Alpha Centauri system. There's 2 stars, Alpha Centauri A and Alpha Centauri B, that are orbiting around each other, and they have a very nice tight orbit. And then there's another tiny little star, which is called Proxima Centauri, which has this huge orbit around the first 2. And I'm going to find Proxima Centauri in our view here. Now, you won't be able to see Proxima Centauri with your naked eye. Oh. Let me type here.
Cute.
There we go.
This is like
There
the universe is Google. Oh, sorry.
Oh, didn't quite go there.
It's my fault. It's my fault. I don't know why, but it's probably my fault.
No, but I really encourage people, if you have a chance, oh, I guess that's it. Okay. To download a stellarium onto your own laptop, and then you can explore the universe and you can see what is in your sky. So I believe this is probably it right there. So it's very tiny. It's a red dwarf star, which means that it's a star that's a lot less massive than our sun. However, in astronomy, the smaller the star is, the longer its lifetime is. So it's going to live a lot longer than our sun. And a few years ago, astronomers found a planet orbiting around Proxima Centauri. And that planet is in the area around the star where water could exist on the surface. So we found an Earth-like exoplanet, the closest it could possibly be to our sun in our solar system, at only 4 light years away. Now, currently, if we tried to travel to Proxima Centauri, we can't travel at the speed of light, so it would probably still take at least a century in order to get to the closest star to our planet, other than the sun. Oh,
Fantastic.
And the other question was, why do stars twinkle? And that is because of our atmosphere. So the light from stars will travel across space, and as in the example of these 2 stars, this light is traveling for 4 years. This light from this star is traveling for 400 years. And that light is nice and good, but then as soon as it hits the Earth's atmosphere, all of our air and our wind and our air currents will mess up that light and distort the light. And so that will cause the stars to twinkle. Now you'll notice that if you're looking towards the horizon, like we are in stellarium here, stars are going to be twinkling more because you're looking through more atmosphere and you're looking through air that's been heated up by our Earth. And so there's more air currents, more disturbance closer to the horizon. But if you look straight up above you, you're going to be noticing that stars won't twinkle as much if you look straight up above.
Right, less atmosphere to interfere with that, right?
Exactly.
Oh, fantastic. Thank you very much, Sky. That's Sky and Kalapana asking those questions. Thank you very much. JD, let's see, from Tall Moon's workshop, they're asking, do gravity waves travel in a straight path, or do they follow a similar path as light? You want to handle that one?
Oh, yeah. I was noticing that. I was just texting Mary Beth about this. So gravity waves are waves. Light is also waves. And so the way they travel will be fairly similar. Okay, so light travels in straight lines as well, generally speaking. There can be interference and things like that. And gravity waves will also tend to travel in straight lines. Sort of think about waves on the ocean. Okay, there you have a wave front and it tends to go in a straight line with this wave front approaching us or moving away from us. Okay, but the difference between gravity waves and light waves is that gravity waves are this stretching and compressing of space and time. So as this gravity wave is coming towards us, the space is compressing in this direction and expanding in this direction, and then it reverses. And so it's this warping of space and time. And you kind of have to wonder, why do we need such a complicated theory? And it turns out that when you look at the LIGO experiments using Newtonian gravity, it doesn't work. You need these gravity waves, this exotic expansion and contraction of the universe. So hope does that answer the question, I hope?
That kind of made sense to me. If it makes sense to me, I think you did well. Thank you.
All right.
Let's see. Our next question is for Claire. Claire, this is from Banyan. Banyan is 12 years old. Banyan is asking, what types of gas does the sun release? What types of gas does the sun release?
The sun, so the sun releases gases of all different types, many different types. Technically, they're not quite gases. So because the sun is so hot, it actually has enough energy in the atmosphere of the sun to strip off electrons. So if you, an atom is the like fundamental building block of everything, and it's made up of different types of elements, and some of those elements are electrons, and they're glued in there pretty hard, and so it takes an awful lot of energy for some atoms. It takes a lot of energy to be able to pull them off and release them into the atmosphere. And side note, that's actually also related to why the sun has a magnetic field, but we won't get into that right now. So the different types of gases that are in the sun's atmosphere are not only the different elements that we might know, like hydrogen and helium and calcium and silicon and iron, but also different species of those. So the one that I think is the most interesting is iron. So the iron, the same as the hard metal that we have here, but obviously it doesn't look like hard metal on the sun because there's so much energy up there. And the sun has so much energy that it's able to pull a huge number of those electrons off. I'm going to show myself up here. I think there's 26 electrons on an iron atom normally. And we have seen, I at least have studied down to iron, which has at least 18 electrons removed, I think. Anyway, the point is that you're able to remove an awful lot of these electrons and then have all of these different subspecies as well. So the way that we're able to identify all of these is when we look at a spectrum. And you may not realize that you've seen a spectrum. It's either, it looks a bit like a rainbow with black slots missing out of it, or sometimes it might look like a series of really spiky lines. And each of those spiky lines, if it's a long wavelength, then each spiky line can refer to one of those specific species. And so we can actually watch how those lines move around and how they grow and shrink. And that's that spectrum then can tell us an awful lot about the behavior and the distribution and the volume and the density of all those gases at different layers of the sun. Because that's the other part, is that it changes quite drastically as you go out in the atmosphere. So we mentioned earlier about the surface of the sun and the opacity change, and that's to do with the makeup of the sun at that particular layer. So as the makeup, the components that are there changes, then the opacity changes, and then all of a sudden we can't see through it anymore, and it looks like a circle for us. So yeah, that's a great question. It was a very convoluted answer, but hopefully I got to it.
I was hanging with you. I was still with you. Thank you, Banyan. Thank you for that question. We really appreciate it. You know, we could go down a wormhole of so many interesting things when we talk about, about awesome light, the sun and stars, but I think we're probably going to have to start wrapping things up, panelists. So I want to thank you so much to you that are watching, but our panel of guests today, and I want to thank you for your time and for your expertise. Dr. Claire Raftery, the Director of Education and Public Outreach at the National Science Foundation's Inouye Solar Telescope in beautiful Boulder, Colorado. Is your mom watching? Is your mom watching?
I don't know. I haven't looked at my phone. I hope so. If so, hello, mommy. And dad as well. My mom and dad are together.
And dad too. We wanted to make sure we pronounced it Raftery, not Raftery.
Well, thank you very much for having me. It was my pleasure to be here. And you know, this is one of the benefits of being in quarantine, right? Is that geography is meaningless. We're able to call in from all over the world to talk together.
Excellent point. Excellent point. Absolutely. And on the island of Maui, we want to thank Dr. J.D. Armstrong, the Maui Technology Education Outreach Specialist for the University of Hawaii Institute for Astronomy. Miss you, bro. I miss you at Astro Day, but it sure is good to see you right here, sir.
I miss you too. And I just wanted to say thank you to all of you. You know, it's an honor to be on a panel with such esteemed colleagues. I'm really flattered that to be on a panel of this caliber and with such an amazing host. Thank you, LD. Thank you, DC.
That's why I have the name here. That's why I have the name in the background.
Yeah.
And well, thank you, JD. Thank you, buddy. And Miss Emily Peavy, astronomy educator at the Imiloa Astronomy Center in Hilo. Thank you, Emily. And I love your enthusiasm. And we love everything about the Imiloa Astronomy Center. So thank you for joining us and representing Hilo.
Yes. Yeah, and if anybody wants to explore some more of the things that Imiloa is putting out, we do have a bunch of online content that we are displaying at Imiloa at Home if you go to our website.
All right, imiloahawaii.org, I believe, right? So
yes, imiloahawaii.org.
Thank you very much. Thanks, Em. And real quick, Kiki is your dog, right? That's Kiki.
Yes.
Kiki. Kiki Kiki must love having you home more than usual, huh?
Oh, yes.
Hi, Gay.
She's I've learned I can't have her with Zoom meetings because she tries to lick my face as I'm talking.
Of course. Well, thanks, Emily. Great to see you. And folks, this wraps up 3 weeks of astronomy or Astro Day celebrations brought to you by the Maunakea Observatories. And they're going to continue to bring us live events just like this one, fun activities and interesting topics as part of their MKO at Home program. Be sure to look for their Maunakea Astronomy Outreach Committee, MKAOC channel. That's on YouTube. Some of you are watching us there. Thank you very much. And follow them on Facebook too at MKOOC. Mahalo, everyone. Thanks again. Stay safe and hui ho. Thank you, panelists. Mahalo. Don't look directly at the sun. Thanks again, gang. Aloha, everyone. Take care and stay safe. Aloha.